Yeah, okay, thank you. So I'm going to talk about machine learning many-body models. So this work is quite a bit different to what's been shown so far in the workshop, but I think it shows that there's a diverse range of applications for machine learning in material science and condensed matter. So we're interested in studying lattice models. So these are used to investigate strongly correlated systems. So for example, systems with F electrons, or if you're studying the Mott transition. So a problem, like these are systems where traditional DFT fails. So a problem with these lattice models is that the number of configurations increases exponentially with number of particles and sites. So diagonalizing the Hamiltonian, this very quickly becomes unfeasible for large systems. So to remedy this, we want to use machine learning. And this diagram here sort of shows our philosophy. So we can generate small systems in large quantities. They're very cheap to make. So we want to try and train machine learning models on these small systems and then transfer this knowledge to larger systems, which are very expensive. And in particular, we want to predict finite temperature properties. So the method I'm going to be showing you, I think, is general for a wide range of models. But as an example, we're looking at the spinless Hubbard model. So we've chosen this because the basis scales better than a lot of other lattice models. So in this, you have, or it's described by this Hamiltonian here. So the first term is a kinetic or a hopping. So if you have an electron on a site, it can reduce its energy by hopping to a neighboring empty site, and it reduces it by t. And then you have an interaction term. So v is the strength of interaction. So if you have two neighboring electrons, the energy increases by v. And then finally, we have the on-site energies by the particle number operator. So for our representation, we use the Hohenberg-Kohn theorem, which has been shown to work on lattice DFT. So we write the total energy as a function of the site occupations. So this is the expectation of the particle operator. So this is our universal function, and then we have a sum over each site, and we take the site occupation by the on-site energy. And so we want to make this independent of the number of sites, because we want to be able to train on a system with a small number of sites and predict on larger. So we write this universal function then as a sum of site-centered local functions. So for example, say we have a lattice with 4 sites, and say we have a subset, we use a subset of 3. Then for each site, we take the first nearest neighbors, and so then we have a total subset of 3. Then we put this into a neural network, and we sum over all the sites, and it's the same neural network. We're using weight sharing. We sum them up, and this is our universal function. And so the size of the subset is a hyperparameter that we have to choose. And then finally, we're using neural networks because, as already mentioned, they're a universal approximator. So they should be able to model any continuous function given enough data. So to generate the data set, so the first step is we choose a lattice size. Then we generate just L, which is our lattice size, L random on-site energies. So with these, then we construct the Hamiltonian, then we diagonalize it. Then from this, we can get the ground state site occupations. And then we work out the universal function, which is again just, we take the ground state energy and subtract the sum of the ground state site occupations by the on-site energies. And so we repeat this process several times to build up a data set, and then we're using the neural networks to map the site occupations, the ground state site occupations to the ground state universal function using the site-centered local functions. So on the x-axis here, I've got the size of this subset, and then on the y-axis is the mean absolute error. And we've got 6, 10, and 14 sites, and then 3 different values of V, which is the strength of interaction. And so you can see that for pretty much for the 3 different lattice sizes, a subset size of about 3 or 5 is sufficient. And then just to give you an idea of what this looks like, for L equals 6, so for 6 sites, and for strength of interaction of 1, and a subset of 3, so that's this point here, this looks like this. So here's the predicted universal function against the exact, and it lines up really nicely on the diagonal, so it's effectively exact. So now the next thing is we take this universal function and we predict on larger lattices. So here we've trained on 6 sites, predicting on 10. Here training on 6, predicting on 14. And then here training on 10 sites and predicting on 14. And then here 0, 1, and 4 strengths of interaction. And then for each of these individual plots, I've got the predicted against the exact universal function. So I think there's 2 takeaways from this. So firstly, training on larger sites increases the accuracy. So if you look at training on 6, predicting on 14 sites compared to training on 10, predicting on 14 sites, there's an order of magnitude difference. And then as well, the error seems to be independent of V. So this was using the on-site or the site occupations as our function in our neural network. But we'd like to start from the on-site energies, as the site occupations are a function kind of the on-site energies. So the on-site energies are really the fundamental quantity. And we can start from the on-site energies by, if we take some on-site energies for some lattice size, and then we take an initial guess for the density. So here we're just using a homogeneous, so the number of electrons divided by the number of sites. So every site starts with the same density. Then we write the energy as our universal function, which is machine learned on a smaller number of sites, and then plus a sum of the site occupations by the on-site energies. And then if we minimize this here, and we just use very simple gradient descent. And by minimizing this, we should be able to get the ground state density, or the ground state site occupations, and the ground state energy. So this is what the results look like. So we took 50 samples for 14 sites. So we started with the on-site energies, and then we used the universal function from 10 sites. So these are the first 4 samples. So on the x-axis is the site, the y-axis are the occupations, and so the dashed blue line is our starting site occupations, so it's homogeneous. We're at half filling, so for 14 sites we have 7 electrons, so each site starts with an occupation of a half. And then the converged, after we do our gradient descent, the converged density is in orange, with the exact in green. And so, I mean, they show very good agreement. And then on the next graph, or on the right-hand side, I'm showing the converged total energy against exact total energy. And so again, it lines up really nicely on the diagonal. So I mentioned at the beginning that we're trying to predict finite temperature properties. So the first step to do that is we have to train a model which will predict the finite temperature properties. So to do that, we start off similarly to the last time. So we take a set of on-site energies, construct the Hamiltonian, diagonalize it, and then so we compute the ground state occupations. And this time, instead of computing the universal function, we get the entire spectrum, and then we can write any operator as a function of t as a sum over the eigenstates by the expectation of the operator by the Boltzmann factor. And so using this, we can compute the entropy, the expected energy, so any finite temperature properties. And then we use machine learning to map the ground state site occupations with temperature to the expectation of this operator at some temperature t. So if you do this on the same lattice size, the results are really good. So I don't actually show them here, but they're effectively exact. So using all of this, you can combine them into this workflow. So the first step is we train 2 neural networks. So we have some lattice size. We train one neural network, which takes the ground state side occupations, predicts the universal function. So from this, we can work out the total energy, or the total ground state energy. And then we train a second neural network, which takes in the ground state side occupations with a temperature and gives out the expectation of some operator at that temperature. So then we go now to a bigger lattice size. We take in some on-site energy, we give in some on-site energies. We then do our minimization, and we get out our ground state side occupations. And then we take these and put them into the second neural network, which gives us the thermodynamic properties. So just taking these, so the 50 converged side occupations, I now put this into my thermodynamic function, and here's the results. So this thermodynamic function was trained on 10 sites, and so here I'm predicting the entropy, energy, heat capacity, and then the side occupation, or the first side occupation, and then we have the color is the temperature. So again, like the entropy and the energy, I think are very accurate. And then the heat capacity and the first side occupation less so, but still, I think very good. So conclusions. So yeah, we've introduced a local site representation. So this is independent of the number of sites. So it means we can train on small, cheap data and use this to predict expensive, large sites. And yeah, there's nothing special about the spinless Hubbard model. We could use any, or really any other lattice model. But then using the spinless Hubbard model, we're able to compute the density from the on-site energies, and we can predict the finite temperature properties from the on-site energies. And then in the future, we'd like to extend to 2 and 3 dimensions and allow the hopping to vary. So this would mean we could do new geometries and new structures, and then also incorporate spin. So if you're interested in any of this, we have a paper out and it's about basically verifying the Hohenberg-Kohn theorem on on the full Hubbard model using machine learning. And then on this new work, there's a preprint hopefully forthcoming soon enough. So thank you very much for your attention.
Hello. Thank you for the very interesting talk. I've got maybe a couple of questions. First is, you compute, you let's say train your neural network on a small lattice, and then you predict some property in the large lattice, and then you see that your predictions are actually accurate with respect to the exact ones which you are still able to compute. Mm-hmm. Now, if you directly compute your predictions on the small lattice, do they still see that they are very much the same as the one you have in the large lattice? I mean, what I'm saying is, wouldn't you be able to just compute the observable directly in the small lattice? And that would still be an accurate, let's say, estimate of the exact observable in the large system. That's the first one.
I don't really know what you mean. Like,
I mean, you compute, if you go to the slide on which you have some properties plotted, no? Yeah, here. Here you have your estimate versus the real value, right, in 14 sites. And your estimate is given by a model fitted on 10 sites, for which you predict a property that is extensive, right? But I guess you plot something divided by the number of sites. Mm-hmm. What if you compute the property directly on 10 sites, and you have the same graph? So not with the, right? Does it make sense?
Yeah, but if you, like, the idea is, like, you might have some set of on-site energies which you can't have in a smaller number of sites.
Right. So but in that case, then you would kind of also feel that when you extrapolate your learned function, right? If you have these finite size effects, basically, right? So what I'm saying is the finite size effects are supposed to be similar in what you learn and in what you then predict on. So if you don't find any error in the observables, then probably you could have computed the observable directly in the small system, or one might think of this in this case, right?
Yeah, I mean, I suppose where I see this being useful is if we could generalize to more dimensions, and then if you had some property that's local, you could train on small number of sites and then start predicting new geometries. So you still have these finite size effects, but hopefully the difference between the geometries would be big enough.
Okay, sure. And actually, the second question would be, what kind of neural networks used for the learning of these local properties?
So
like how many parameters have you got?
It's 128,
128.
2 layers and then an output layer.
Okay. So, right. Now, because I'm thinking essentially if you learn something that is only a function of 5 numbers, let's say, and these are, that can be only in a few states, you know, you could as well tabulate all the possibilities, right? And that would be of the order of 100 or so, essentially. So for that kind of system, one might just have a simpler representation, or might just like a tabulated function, and then you might just assign a number for each possibility. I don't know.
Yeah, but like it's a continuous function dependent on the density, so...
It is continuous. Okay, sorry.
The last question, and the next speaker can put the...
I didn't see the ratios that you were using, but typically it's interesting to study the case where V is much larger than T, right?
Right.
You have strong correlations, and even it's, I think, could be more interesting when you have strong correlations on site, because you use only a low interaction between next neighbors, right?
Yeah. We had T set to 1.
So it will be as nice as your fitting will be with this change in the parameters as we saw?
Sorry, if we had larger on-site.
Yeah, large on-site or...
like if I had to guess, I think it would be more accurate because larger on-sites I think would mean it's more localized. But that's just a guess.
Okay, thanks.
Okay, if there is no more question, let's take a speaker.